Good morning, everyone. So we are discussing about the modeling of membrane modules, and first we took the laminar flow regime and Newtonian flow through a spiral wound module. Now the spiral wound module and the flat plate and frame modules both can be analyzed by taking recourse to rectangular coordinate system. On the other hand, the tubular module will be and hollow fiber module can be modeled using the polar coordinates. Okay. So, in the last class we have seen in detail how the various complexities can be added to the analysis, and first we considered that the permeation velocity, the permeate flux will be constant. In second case, we have considered it is proportional to delta p, but it is transmembrane pressure drop, but it is the osmotic pressure effects are negligible. In the third and the more realistic analysis that we have considered in the last class, that is case number 3, is that the osmotic pressure is not really negligible and it is substantial. Under these conditions, how the membrane module design can be carried out. Okay. So, we have considered in the last class, we have just finished how to do the modeling or analysis in case of rectangular coordinate system that is applicable for the plate and frame and spiral wound module. In today's class, we will start with the tubular module. Okay. So, here let us write down the governing equation. The governing equation for the tubular module, governing equation of transmembrane pressure drop is d delta p dx is equal to minus 32 mu u by d square. Okay. In fact, this comes from the Navier-Stokes equation. Equation of motion for a flow through a tube. Now, this will be the governing equation from delta p, and the governing equation of cross flow velocity becomes du dx is equal to minus 4j over d. D is the diameter. Now, how to obtain this equation? In the last class, we have really did all the derivations in detail. What we did, we took an infinitesimally small element and did an overall material balance. That will lead to this expression, that is a governing equation for cross flow velocity. And if you really do carry out a differential analysis over a differential element, in terms of solute concentration or in terms of solute balance, you will be getting the concentration balance equation, and that will become u del C del x is equal to 4 j by d C minus C p. So, del C del x will be 4 j over d u C minus C p. So, these will be giving you the concentration balance equation, governing equation of concentration in the bulk. Now, we know the mass transfer coefficient, and this bulk concentration C and membrane surface concentration Cm they are related by an algebraic equation via the definition of mass transfer coefficient. In the last class, we have derived that expression in detail and we have written it down and we have understood how to get that expression. So, you will be getting a relationship between the bulk concentration and membrane surface concentration C and Cm via the definition of mass transfer coefficient. It will be an algebraic equation that we have already seen earlier. Now, in that expression, you will be having the expression of mass transfer coefficient K, and mass transfer coefficient K for a turbulent flow regime becomes 1 over I u d square by dx raised to the power 1 upon 3, where the integral I is given as, it is a definite integral. In this case, it becomes exponential minus 8 phi cube over 9 minus 2 by 3 lambda phi d phi, where lambda is nothing but P w divided by Reynolds Smith d by L raised to the power 1 upon 3. Okay. Now, where from you get this equation? In fact, we have carried out the similarity solution for the rectangular case, and we have derived the expression of mass transfer coefficient, and you can carry out the same analysis in a tubular module and under the laminar flow conditions, then you will be getting this expression. In fact, if you are really interested, you can look into the reference of Day and Bhattacharya, Journal of Membrane Science, volume 109, year 1997. Okay. I think the page number is around 109 to 115 or 16, whatever it is. So, just look into this reference. In this reference, there are 3 geometries have been solved. One is for the rectangular geometry, another is the tubular geometry, another is the radial cell or radial geometry. In the class, we have derived the full expression analysis of rectangular geometry. Okay, just look into this reference and see how the radial tubular polar coordinate has been solved, and you will be getting this expression of mass transfer coefficient as a function of x there, and the definite integral, the form of the definite integral will be taken this form, and this P w is nothing but it is the length average in terms of length average permeate flux. That means, this P w is nothing but J bar d over d, this non-dimensional permeate flux. Now, again the algorithm that we have discussed in the last class, that will still hold good in this class as well. We will be assuming a value of length average permeate flux, and then calculate the we will solve 3 ordinary differential equations coupled with one algebraic equation that has to be solved at every step of that has to be solved iteratively at the every step of Runge-Kutta 4 algorithm for the solution of ordinary differential equations. Okay. So, in that case, you will be getting the profile of permeate flux as a function of x, do a length averaging and check whether the calculated length average permeate flux is equal to the assumed value or not. If not, you have to iterate number of times. Within 3-4 iterations, you will be getting the solution. So, that goes for the the laminar flow conditions under the tubular flow module. Now, we will just look into some of the aspects of if the flow is turbulent. That means, till now we have done the analysis in laminar flow conditions. That means, Reynolds number is less than 2200, that is the laminar, and Reynolds number greater than 4000, that will be the really turbulent flow. Now, in this case, what we have to do? We have to do an overall the transmembrane pressure drop, governing equation of transmembrane pressure drop. If you remember how we obtained in the last time, this is a turbulent flow. So, governing equation of transmembrane pressure drop will be no longer the way we have obtained earlier. That will be obtained by doing an energy balance equation over a differential element. Okay. So, that means you are considering an element that is located at x plus delta x, where the pressure becomes P here, this becomes P plus delta P here, and U becomes U and U plus delta U, C becomes C plus delta C, something like that. Now, you have to write down the overall energy balance equation. On this differential element of the module. If you do that, I am just writing the final expression. You just go into your textbook and see whether you will be able to derive this equation from the fundamental equations of energy balance. Okay, that is P minus P plus dP. dP is basically the delta P, that is the P plus dP is the pressure at the outlet of the elemental differential element, plus rho u square by 2 minus rho u plus du square divided by 2 plus A m by q times j rho by 2 u square minus j square is equal to 4 rho f dx u square by 2 dE. If you remember, this becomes this is a pressure variation term, delta P by rho, pressure term. These two becomes the kinetic energy term. This is pressure energy, this is the kinetic energy, and again this term is associated with this kinetic energy of the change in kinetic. This is basically change in kinetic energy. This change in pressure energy between the inlet and outlet, this change in kinetic energy of permeating stream, and this becomes a pressure loss term, friction loss term. Okay, this becomes a friction loss term. Okay, so this equation finally will take this form. I am just writing the final form. What you can do, you can divide both sides by delta x, okay, and really make it into a differential form. This becomes d delta p dx. Delta p can be written as p minus p atmosphere. So, dp dx can be written as d delta p dx, where delta p is the transmembrane pressure drop. D delta p dx minus rho u du dx plus Wj. W is the width of the module or the channel, Q is the flow rate, rho u square minus Wj over Q, rho j square minus rho f u square by 2h, okay, where Q is nothing but 2 Wh times u. 2h is basically the full height, W is the width, 2W is nothing but the normal cross section of the against the flow, u is the velocity. So, this becomes the flow rate, okay, and F is the friction factor. Now, once you do this, then you will be getting the final form of pressure balance equation, the final form of governing equation for delta P becomes d delta P dx is equal to rho by 2h 3 u j minus j cube by u minus f of u square, okay, where f can be is basically friction factor for a smooth pipe. It is you can use Blasius's formula, right. You can use Blasius's formula as f is equal to 0.079 divided by Reynolds raised to the power 0.25, where Reynolds number is based on the equivalent diameter, okay, rho u0 d by mu. Okay. Now, this is not u0, this will be u. Okay. So, bulk velocity. So, this is the fanning friction Blasius formula. Now, for the if the pipe surface is rough, so you can have various expressions of friction factor in terms of roughness, surface roughness. If you remember the von Karman's chart, okay, or Blasius chart. Now, in this case, the mass transfer coefficient and your governing equation. So, that gives the governing equation of delta P. The governing equation for u and c, that means bulk velocity and bulk concentration, can be obtained by the overall material balance and overall species balance over the differential element that we have already analyzed earlier. Okay. Governing equation of u can be obtained by material balance, and governing equation of c will be obtained as solute balance or species balance equation over the differential element. Of the module that we have already discussed earlier. Only thing is, in this case, what is new? The newness of this, the novel thing in the turbulent flow is that your expression of transmembrane pressure drop, governing equation of that will be changed from the laminar flow, and it will be obtained from the overall energy balance within the over the differential element. Okay. Now again, what you have to you have here, the if you really would like to get the value of the permeate flux and permeate concentration, you must be having an expression of that relates an expression relating bulk concentration C and membrane surface concentration Cm, that we have already obtained by the we have already seen that an algebraic equation connect these two. Algebraic equation connecting C and Cm via the definition of mass transfer coefficient. Okay. This mass transfer coefficient for the turbulent flow this mass transfer coefficient can be expressed as a function of x, and in this case it becomes 0.236 d divided by I Reynolds raised to the power 1.75 Schmidt divided by d square times x whole thing raised to the power 1 upon 3, and I is given as 0 to infinity exponential minus eta cube by 3 minus 2.82 lambda eta d eta, where lambda is the suction parameter, is defined as Pw divided by Reynolds Schmidt d by L raised to the power 1 upon 3, and this Pw average will be defined on the non-dimensional length averaged permeate flux. That means, it becomes J bar d over d. Okay. Now, the everything is now falling in and how you obtain this expression. Again, this expression we have not derived in the class. If you are really interested, you can look into the reference of this work, Minikanti et al. It also came in Journal of Membrane Science in the year 1999. Okay. Just give a search to Science Direct in Journal of Membrane Science, Minikanti et al. On 1999, you will be getting the article. Okay. In that article, you can look into how we have derived the turbulent, how we have simulated the turbulent flow, and I will give you the rough idea of how we really did the turbulent flow modeling. In fact, what we assumed a fully developed turbulent velocity profile. Okay. And we know that the turbulent velocity profile will be having 3 components. One is the viscous sublayer, another is the transition region, another is the fully developed turbulent core. And we have assumed that our so there is the fully developed velocity profile. Now, we have assumed our mass transfer boundary layer lies within the viscous sublayer. That means your viscous sublayer, if you remember that it lies between a non-dimensional distance from the wall up to a height of around 4 or so. Okay, I do not remember it, some value. Okay. Now, after that it becomes a transition region, then it becomes a turbulent core. Now, within that region, if your in most of the membrane based separation processes, we are talking of filtration of the proteins and higher molecular solutes, which will be having very low diffusivity. If you have a very low diffusivity, your thickness of mass transfer boundary layer is, since it is inversely proportional to the diffusivity. So, so it is directly proportional to diffusivity. So, mass transfer boundary layer thickness will be extremely small. Okay. So, therefore, we in these particular cases where these solutes are considering in the membrane based separation processes, the thickness of mass transfer boundary layer will be extremely small. That means, we are assuming the thickness of this mass transfer boundary layer or concentration boundary layer lies well within the viscous sublayer of the fully developed turbulent velocity profile. Okay. So, in that, under this assumption, the whole thing becomes very simplified and it can be recast on the form of similarity solution that we have already derived earlier. That means, you will be getting a parabolic partial differential equations with a boundary condition residing at infinity. Okay. So, again you will be going to have a similarity solution and you will be getting this expression. Okay. So, please, if you are interested, look into this paper and get into the derivation, and you can really do the derivation by yourself, because it is almost semi analytical in nature. Okay. So, again in this case we will be assuming the, so basically again we will be assuming we will be getting 3 governing ordinary differential equations, 3 governing equations for 3 quantities. One is the transmembrane pressure drop, another is the bulk velocity, cross flow velocity, another is the bulk concentration. This and bulk concentration and membrane surface concentration will be connected via an algebraic equation through the definition of mass transfer coefficient. So, these 3 ordinary differential equations and one coupled algebraic equation constitute the DAE system, DAE IVP system, that means differential algebraic equation system, and that is initial value problem. Okay. And this can be solved by using RK4, and at every step of RK4 you have to evaluate the nonlinear algebraic equation by using Newton-Raphson and update the value of Cm. So, you will be getting a profile of membrane surface concentration, you will be getting a profile of permeate flux, you will be getting a profile of permeate concentration as well, because permeate concentration can be expressed as Cm into 1 minus RR, real retention. So, if you know the value of Cm, you will be able to calculate the value of Cp. So, once you get a value of a profile of permeate flux, you can do a length averaging by using Simpson's rule or 1/3 or 3/8 or whatever, or trapezoidal rule, whatever, and then you will be getting the length averaged permeate flux and check whether that value calculated value coming close to the guessed value or not. Otherwise, you have to reiterate a number of times. So, that is how one have to do the module modeling under the turbulent flow conditions. So, so those who are not present in the last class, again I will emphasize why this module modeling becomes very important. If you remember, in the earlier classes we never talked about the module modeling, we talked about the constant delta P, constant transmembrane pressure drop, but the transmembrane pressure drop can be considered as constant if we are talking about a length of, let us say, few centimeters, let us say 10 centimeter, 30 centimeter, like that, but actual membrane module is of larger in length. For example, it can be anything between 1 meter or higher. 1 meter means 3 feet already. Okay. So, therefore, in that over the length of the module there will be drop in delta P. So, you must be taking care how the pressure drop profile varies as you go along the length of the module, because based on that you must be selecting a pump that will be pumping the whole flow, liquid into the system, maintaining the delta P, which will be quite large, because under the delta P there will be permeation occurs, because the filtration will be under the delta P. But also at the same time you should be very careful about that whether the loss in pressure at the outlet of the module will sustain that pressure, so that you will be getting the some significant amount of permeation. So, pressure drop becomes very important in all the chemical engineering unit operations that I mentioned earlier, starting from fluidized bed reactor, packed bed reactor, distillation column, absorption column, including the membrane module. So, therefore, that is the need to calculate the governing equation of transmembrane pressure drop. In the same way, you can calculate the you can formulate the governing equation of the bulk velocity, you can formulate the governing equation of bulk concentration, and there lies the requirement or necessity of doing modeling of the actual module. Okay. And for a platen frame and spiral wound module, you have the coordinate system that you are going to adopt, it is rectangular coordinate system XYZ. For a tubular or the hollow fiber system, you are going to adopt the radial polar coordinate system. Okay. But the point is, under these circumstances, radial polar coordinate system will be boiled down to rectangular coordinate system, simply because the thickness of boundary layer that we are considering in this case will be in the order of micron. Okay. And the actual dimension of the model becomes higher. So, in that case, if you neglect the curvature effect, that means you are standing in front of a big sphere, and if you stand very close to it, you cannot experience the effect of curvature. The surface in front of you will be appear to you as a flat surface. So, the thing becomes similar. The thickness of mass transfer boundary layer is so small that when you are talking about suppose you are standing inside the mass transfer boundary layer looking at the wall, so it becomes a flat surface. So, under the situation that whatever we are doing here, instead unless and until we are talking about hollow fiber module where the thickness will be pretty small, in most of the other cases tubular modules etc., the analysis will basically boil down to the flow through a flat plate, okay, because of the loss of curvature effect. And why the curvature effect will be lost? Because the mass transfer boundary thickness will be extremely small. Why the mass transfer boundary thickness will be extremely small? Because we are talking about a system where speed number will be pretty high. Why speed number will be pretty high? Because the diffusivity is pretty low. Why the diffusivity is pretty low? Because you are talking about a solute which will be having very high molecular weight and low diffusivity. Okay. So, that is the rationale of doing the module design in a comprehensive manner. Okay. Then we will go to the next membrane based separation process, that is dialysis. Now, in dialysis, the driving force is the concentration difference. Till now, we have looked into the pressure driven membrane based separation processes. For example, reverse osmosis, it requires very high delta P, the operating pressure. It is generally in the order of 25 atmosphere to 40 atmosphere or even higher. Then we talked about the nano filtration, where the pressure requirement becomes lower, and it will be in the order of let us say 10 to 12, 10 to 15 atmosphere. For ultrafiltration, since the pore size is larger, the pressure requirement will be further lower and it will be around 6 to 7 atmosphere. For microfiltration, almost around 2 to 4 atmosphere will be sufficient. But in case of dialysis, we require no pressure difference, and the only driving force is the concentration difference. Okay. And dialysis has very tremendous and useful and important applications. Applications is basically the dialysis, human dialysis. Okay. Here we are basically removal of toxic materials from the blood like urea, creatinine. Now, they will be having lower molecular weight. So, we have to select a membrane which will be around in the order of let us say 3000 to 4000 cutoff, or even let us say in the order of 10 to 12,000 cutoff molecular weight. Here we just send the dialysis in the feed chamber, and on the other, and basically the dialysis membrane will be kept between two chambers. One will be the feed side, another will be the dialyzed side. Dialyzed side, the fresh solution or distilled water or saline water will be circulated, and in the feed side the blood will be circulated. Okay. Now, blood cells etc. will not be permeating through the membrane, because membrane portion is pretty small. Only the urea, creatinine, these small molecular weight elements will be eliminated from the feed site and they will be transported to the dialysate site. So, therefore, dialysate the concentration of urea, creatinine etc. will be increasing from the in the dialysate site. So, basically in generally in the hospital, what they do, they from an overhead tank they circulate the fresh dialysate. What is the fresh dialysate? It is basically a distilled water solution. It is not pure distilled water solution. It is basically a water with a composition of the of blood, that means salinity etc. maintained without the blood cells. Okay. So, in that case you are maintaining the maximum concentration difference, right. If you are sending the fresh dialysate in the dialysate site, then the concentration of the urea, creatinine at any point of time or at any location will be equal to 0 there. So, there you are maintaining the maximum concentration difference, so that the transport rate of urea etc. toxic materials from the feed site or the blood site to the dialysate site becomes fast. And typically dialysate, what is generally done is basically dialysate, the whole system is called, it's composed of hollow fibers, the small hollow fibers, and the housing is basically hollow fiber membrane cartridge or module. Okay. And these modules we are not really fabricating in India, we are basically getting these modules from outside, all the Korean modules, Korean, Japanese, French and German. Now, based on the fabrication company of the manufacturer, the cost varies from between 1500 to 2500 rupees, and a kidney failure patient, he requires dialysis 3 to 4 times a week. Okay. But these cartridges are generally used for one time, basically use and throw type. But in India, since they becomes costly, doctors use them number of times for the same patient, 3 to 4 times. But every time its efficiency gets lower and lower because of the blockage. Okay. Now, the point is Varun is one of the students under me we are trying to develop the dialysis cartridges on our own. So, if we can really do that, then we can supply the dialysis cartridge at a very cheap rate. We got some success, but this will be tested and they will be basically tested and finally tested by the doctors who will be prescribing them. Okay. But this testing cannot be done on human directly, there will be several stages to do it. Anyway, so there are several applications apart from the medical application, there are several other applications of the dialysis as well, industrial applications. In these industrial applications, in most of the applications are in pharmaceutical sectors. Purification of proteins. Now, in a stream, a particular, suppose you are targeting a particular protein, it will not be a pure protein, it will be mixed up with some other proteins or small molecular materials or solutes. They can be separated separated by dialysis. There are several other industrial applications as well. Now, let us look into the principles of dialyzer. Let us first look into a schematic of a batch dialyzer. This is a batch dialyzer, this is a feed chamber and this is a dialyzer chamber. And here we put the dialysis membrane. So, because of in the dialysis chamber initially there was no concentration of the solute, solute concentration was equal to 0 and the solute concentration is maximum in the feed. So, solute gets transported across the membrane and go to the dialysate site. So, the concentration gradient gradually decreases. So, if you look into the concentration versus time in the feed site, concentration of solute versus time in the feed site, it will go on decreasing. And it will go on decreasing asymptotically. Okay. Because you are not maintaining the dialysate concentration, the maximum concentration gradient here, because the dialysate, you are not doing any recirculation or recycling. Okay. On the other hand, in case of continuous system, In continuous system, this is the feed in, this is the feed out, dialysate in, dialysate out. Okay. Now, there is another problem in dialysis is that if you would like to remove a small molecular material, for example, urea, creatinine, etc., you have to select a pore size of the membrane such that they will be permeable. Now, any membrane cannot be having a very sharp pore size distribution, sharp molecular cutoff. So, since it will be having a distributed pore size, there will be a pore size distribution, not only along with the urea creatinine, some amount of serum will also be transported from the feed side to the dialysate side. So, there will be a loss of vital body fluid. So, so if you select a higher pore sized membrane, the transport of urea creatinine will be much smoother, much easier, much faster, but at the same time loss of vital fluid. But if you select a very small pore size of the membrane, the transport, the loss of vital fluid will be minimized, but at the same time the transport of urea, creatinine, etc., will be constricted. Okay. So, there will be hindered diffusion or hindered transport. Okay. So, there should be a judicious selection of this of these two aspects, the pore size and the selection of the membrane. Now, the thing is, now in general what is done, in general, in order to have a, if you put a patient under dialysis, in fact basically you are taking the blood out of the body and again recirculating it. So, the patient cannot be having that much patience or that much stability if you carry out the dialysis over a long period of time. So, generally dialysis is typically carried out for about 45 minutes to 90 minutes, okay, anything between that. So, therefore, what people used to do, people used to select a larger pore size membrane, so that the transport of the urea creatinine will be maximized, but at the same time you will be facing a loss of body fluid. So, there will be, they inject makeup body fluid, okay, to the human system. Okay. So, that is how it is maintained. In a continuous cell, in a continuous system, the direction of circulation of feed and the direction of circulation of dialysate circuit, it will be in the opposite direction in order to have the maximum efficiency in your system. That means, this will be a counter current operation. That means, the direction of the feed will be in this direction, the dialysate circuit will be in the opposite direction across the interface of the membrane. So, this will be having a counter current operation. To ensure maximum efficiency. Okay. Now let us look into let's go into the details of the dialysis system. Let us look into the transport mechanism, etc. Main transport mechanism in dialysis is concentration difference in concentration gradient. Okay, the concentration gradient. What is the concentration gradient? What it will cause? It is basically triggering the diffusion of the solutes. Okay, so main transport mechanism is diffusion. Ni, we write it as mass flux or molar flux. It depends on the unit of concentration that you are selecting of ith species. This is nothing but dim dcim dx. Okay. What is dim? Dim is diffusivity of ith solute through the membrane. L is the membrane thickness, and CIM is concentration of ith species in membrane phase. Okay. So, with this we can so basically there is a concentration difference across the membrane that triggers the diffusion of the solutes through it. Okay. So, we can write down the Ni as DIM over L CIM F, that is in feed side, minus CIM in the dialyzed side. Now, there is a difference in, again whenever there is a transport across the membrane, some solutes will be transported here. So, there will be a film of solutes that will be formed both in feed side as well as the dialyzed side. What is this film? This film is nothing but the mass transfer boundary layer. Okay. Beyond this, this SIMF basically the concentration of ith species on the membrane surface in the feed side, and CIMD is nothing but the concentration of ith species on the membrane surface in the dialyzed side, and this is the bulk of the feed, this will be a bulk of the dialyzed. Between the bulk and the membrane surface there will be a formation of thin boundary layer, mass transfer boundary layer. Okay. So, we assume that the ratio, the value of solute concentration and in the bulk from between this point there is no concentration gradient, right, these flat, between this concentration between this point and this point it is defined by a partition factor. Okay. So, it is nothing but some kind of mass transfer coefficient that we will talk later on. Okay. Let us say that the concentration between bulk and on the membrane surface is related by a partition factor. Okay. And this partition factor, let us say Mi for the ith species. So, therefore, CIM F over CIF is equal to Mi is equal to CIM D divided by CID, where CIF and CID are bulk concentrations in feed and dialyzed. That means, we are simply assuming right now that the bulk concentration in the feed side and the dialyzed side and the surface concentration of the solute at the feed side and dialyzed side is related by a simple partition coefficient or partition factor. Okay. So, therefore, using this definition you can relate what is the rate of transport of the solute from the feed side to the bulk, from the feed side to the dialyzed side in terms of bulk concentrations, right. That means, you are going to replace CIM in terms of CIF and CIMD in terms of CID. So, therefore, Ni is nothing but DIM by L Mi CIF minus CID. Why you are doing this? Because these concentrations are measurable. You can measure this concentration because you can take a sample and do a measurement, do an analysis, okay, either spectrophotometrically or refractive index or whatever. So, these are measurable quantities. So, if you know the value of DIM, if you know the value of M, if you know the membrane thickness, if you measure the bulk concentration, dialyzed concentration, you can estimate what will be the molar flux, how much, what is the unit of this? This will be kg per meter square per second. If concentration is expressed in kg per meter cube, this will be molar per meter square per second if concentration is expressed in molar per meter cube moles. That will simply indicate why this is very important. This is important simply because if you know the membrane area, if you can calculate this thing Ni, if you know the membrane area, because that is basically macroscopic property, right. If you know the membrane area, you can calculate how much solute will be transferred from the feed side to the dialyzer side per unit time. So, if you have a target that I have to remove in 1 hour, let us say 10 milligram of urea, then what will be the membrane area I am going to select. So, that will give you directly a design aspect. The value of Mi is 0.5 for urea solution and regenerated cellulose. That means, if your membrane material is regenerated cellulose, and if you are talking about urea aqueous solution, the value of Mi is 0.5, and DIM will be in the order of 10 to the power minus 11 meter square per second. Okay. How to calculate DIM? That it is very easy to calculate diffusivity in the bulk, but if you would like to find out diffusivity in the membrane phase, that will be quite complicated. How to do that? That we will see later on. Okay. Another estimation, okay, for phenol, Mi is equal to 0.01 if polyethylene is membrane material. So, it is a function of membrane material as well, and this is equal to 17.5 if ethyl cellulose is the membrane material. So, there are certain literature values available for a particular solute and membrane material combination. Okay. Now, let us look into how this DIM can be calculated, determination of DIM, because that is very important. So, if you would like to calculate the solute flux, you can measure the concentration in the bulk as a feed side in the dialyzer side, both are experimentally measurable. If you know the literature value, you can know the value of what will be the value of Mi, but you should know the value of DIM as well, that is the diffusivity of the solute in the membrane phase. There is a relationship given, DIM is equal to DIB epsilon divided by tau and multiplied by a drag factor, drag coefficient F drag. Okay. DIB is nothing but diffusivity of ith species in the bulk, epsilon is membrane porosity, tau is the tortuosity factor, because all the pores are not straight cylindrical pores, there will be tortuous pores and they will be interconnected, and the drag coefficient F drag can be written as let us say particle radius, solute radius is Ri and pore radius is Rs, then it is given by this expression 1 minus 2.1 Ri by Rs plus 2.09 Ri by Rs whole cube minus 0.95 Ri by Rs raised to the power 5. Okay. Some kinds of relations are provided if you know the radius of the solute and radius of the pore. Now, using this definition of DIM, it is very difficult because all the parameters that are mentioned, those are involved in the definition of this quantity, they are extremely difficult to measure. For example, the tortuosity factor, you cannot directly measure the tortuosity factor, there are some thumb rules the value will be in between 2 to 4. Okay. Similarly, the membrane porosity, it is extremely difficult to find out the membrane porosity. Okay. So, diffusivity of ith species in the bulk may be measurable or may be available in literature, that is quite simpler. On the other hand, the solute radius is measurable, but the pore radius is very difficult because the pore sizes will not be a single pore size, right. So, there will be a distribution of the pore size. So, you must be talking about the average pore size. So, again that is difficult. So, anyway, if somehow you can measure these quantities, one can use this relationship in order to determine the value of DIM. Typically, the value of DIM will be at least 2 to 3 orders of magnitude less. That means, if you have a bulk diffusivity 10 to the minus 11 meter square per second, the DIM will be in the order of 10 to the minus 12 or 10 to the minus 13 meter square per second. So, that idea should be, it should not be 10 to the minus 26. Okay, that should be the idea, that 2 to 3 order of magnitude, 1 to 3 order of magnitude will be less in the membrane phase compared to the bulk phase. On the other hand, the parameters involved in calculation of the diffusivity through the membrane phase is complicated, they are difficult. So, there are other, so in order to avoid that, what one can do, one can conduct a separate set of experiment, like how we determine the permeability, how we determine the real retention of the solute. Exactly the same way we can conduct the batch dialysis experiment, and by looking into the concentration profile, one can estimate the value of DIM, that we will see later on. Okay. So, therefore, you see that even in the case of dialysis, like the membrane filtration, like we have discussed earlier, reverse osmosis, ultrafiltration, etc., the batch operation, although it is a worst performer, it is very important. Why it is important? To extract some of the interesting and important kinetic parameters. Okay. So, we will stop here and we will continue in the next class.